Hello everyone, happy to see you here. Welcome back to my channel, Hi Mathematics. Today we have very interesting, I would say like tricky algebra question, 1 to the x equal to 5. And a lot of students may be thinking that this is not possible because we learned that 1 to the power, like very huge power, we can consider, for example, 1 to the power 100 equal to 1. And we are talking about 1 to the doesn't matter what the power equal to 1. So in terms of math, it's not possible. It looks like that. But right now I'm going to show you a few thoughts. How can we find at least one root? So if you're sitting, for example, on your exam, you can easily apply a natural log on both sides. You can easily do this. So natural log of 1 to the x equal to natural log of 5. So you just apply natural log on both sides. Right now, this x will come down right here because in terms of like log property, so we have x times natural log 1 equal to natural log 5. And right now the final step, let's divide both sides by natural log 1 because we need to find only our x. So let's do this right now. As a result, we have x equal to natural log 5 over natural log 1. And right now you can easily prove that right here we don't have real number root because we can easily find natural log 5, this like some constant, I don't know exactly what it's equal to, but natural log 5 is a constant, but natural log 1 is equal to 0. So right now at this point you can easily write that right here you don't have no real roots. In terms of like this, in terms of this way, how can we write it? But as I said before, I'm going to show you a few tips, few really interesting tricks, few prompts. How can we find at least one root? Right now you can see, okay, we don't have right here real number root, but maybe complex root. For this, I'm going to write a really interesting identity which helps us a lot. This identity, this Euler's identity looks like that. So e to the power I times theta equal to cosine theta plus I times sine theta. This identity works perfectly. We can easily prove it real quick. For example, let's check it when theta, for example, for theta equal to, for example, 0. Let's see what will happen when theta equal to 0. As a result, what do we have? E to the power I times 0 equal to cosine 0 plus I times sine 0. And of course, sine 0 equal to 0, so we have 0 right here. Cosine 0 equal to 1. And right here we have on the left side we have 1 as well because e to the power 0 equal to 1. So as a result we have 1 equal to 1. So this identity works perfectly. This identity is great for us. But I don't need this identity. I'm going to use one really important substitution. So just look at my substitution that I'm going to use. My substitution looks like that. So my substitution let theta is equal to, let's use this substitution, theta equal to 2k pi. We are talking about k integers, we are talking about k is from z, and we are talking about k is 1, 2, these integer values. We are talking about positive ones, so 1, 2, 3, and a lot of these cases. So let's use this substitution. Instead of this theta right here, let's plug in this one. Okay, let's do this right now. As a result, how does our substitution looks like? How does our expression looks like in this moment? So e to the power I times 2k pi equal to cosine 2k pi, 2k pi, and plus I times sine 2k pi. So in terms of this substitution, we have this expression. Instead of theta, we plugged 2k pi, and we have this expression. This is extremely important expression because right now we're gonna do a really important moment. We're gonna try to see what will happen when k is equal to 1, 2, and 3, and of course a lot of these cases. And right now a really interesting thing because, for example, we start with k equal to 1. So let's do this right now. So for k is equal to 1. Let's see what will happen when k is equal to 1. As a result, what do we have? E to the power I times 2 pi equal to cosine 2 pi plus I sine 2 pi. But this cosine 2 pi and sine 2 pi, we can easily find it because this is like trigonometrical stuff. So cosine 2 pi, this is cosine 360 if you're talking about degrees, and everyone knows that this expression equal to 1, and sine 2 pi equal to 0. So this one equal to 0. And when we add 1 from here plus 0, with result we have 1. And just keep in mind this 1, okay? So with result we have 1. So e to the power I times 2 pi equal to 1. Right now let's see what will happen when we're gonna plug in, instead of k, we're gonna plug in so k equal to 2. Let's see what will happen. So as a result we have e to the power I times 4 pi equal to cosine 4 pi okay, cosine 4 pi, plus I sine 4 pi. Now we have this expression we're gonna plug in. Instead of k we plugged 2, and as a result we have 4 pi and 4 pi right here. But cosine 4 pi, we're talking about a period, so this looks like 360. We're talking about one more period, so we're talking about the same meaning, so the same 1 right here and the same 0 right here. Okay, in terms of period it changed nothing. Okay, 2 pi, 4 pi, 6 pi, we're talking about even values. 2, 4, 6, so it changed nothing. We're talking about the same 1 plus 0. So as a result we have the same 1 on the right side. So as a result we have 1 right here and 1 right here. Really great. Right now let's test one more thing. Let's test k equal to 3. This is the final expression for us. So 4k is equal to 3. Let's see what will happen. And I really hope you see right now that we have e to the power I times 6 pi equal to cosine 6 pi plus I sine 6 pi. And if you look closely, sine 6 pi equal to 0, we are talking about the same period, and cosine 6 pi equal to 1. So 1 plus 0 equal to 1. And I really hope you see this pattern. This pattern looks like that. Doesn't matter what do we have on the left side, so we're talking about only when k is integer. Doesn't matter what do we have right here, e to the power I times 2 pi, e to the power I times 4 pi, e to the power I times 6 pi. Doesn't matter what do we have on the left side. This left side, when k is equal to integer value 1, 2, 3, 4, all the time this expression on the left side is equal to 1. Okay, we have 1, 1, 1, and if you look closely, we will have e to the power I times 8 pi equal to 8 pi, 8 pi, 10 pi, 20 pi, 24 pi. We're talking about this period, and all the time this period gives us 1 on the right side. Okay, so this expression on the left side, we're talking about general case, so we're talking about this expression all the time equal to 1 when k is integer. So this is extremely important moment right now. So this expression e to the power I times 2k pi, so from here e to the power I times 2k pi, this expression all the time equal to 1, but when k is integer. So when, or but, we need to write that k is integer. This is extremely important moment, because when k is not integer, for example, real number value like 1/2, 1/3, we don't know what will happen there, but we're talking about k is integer. So right here at this moment, so k is integer, let's write something like that, 1, 2, 3, and a lot of these values. Okay, this expression e to the power I times 2k pi equal to 1 when k is integer, but don't forget about expression from the beginning, because in the beginning we had 1 to the x equal to 5. And right now, really important moment. We know that right here we don't have real number roots. We know exactly that we don't have it because we proved in the beginning we had this natural log 1 in our denominator. So we know that right here we don't have real number roots, so everything is great. And maybe we have complex root, and that's why it's really great to apply this expression instead of 1, because we have this I, this complex value. So it helps us a lot, because it looks like we don't have real number roots, so maybe we will have complex roots. So this is like one or two cases. So this case we don't have it, so we need to consider our complex value, and we have right here this complex value, so this expression with the complex value I equal to 1. So instead of this 1, let's plug in this e to the power I times 2k pi. So as a result we have e to the power I times 2k pi instead of 1 raised to the power x equal to 5. Okay, so I really hope you understand it. Instead of 1, I plug this e to the power I 2k pi. Right now, let's simplify it. Of course, we can easily raise this to the power x. We will have e to the power I 2k pi x equal to 5. Right now, let's apply natural log on both sides. Okay, let's do this. So natural log of e to the power I times 2k pi x equal to 5. And in terms of natural log property, this power, this big, like huge power, will come down right here. So as a result, we will get like I times 2k pi x times natural log e equal to 5. And of course, right here, natural log, I forget a little bit about it, right here, natural log 5, don't forget about this right side, because I apply on the left side, we need to apply on the right side as well. And as a result, what we get from here, natural log e equal to 1, so as a result, we have I times 2k pi x equal to natural log 5. And we need to find from here, we need to find our x. Of course, we need to divide both sides by this expression, I times 2k pi. As a result, we have I times 2k pi x divided by I times 2k pi equal to natural log 5 over I times 2k pi. Of course, from here we can easily cancel it. And as a result, we have our, looks like our answer. We have x equal to natural log 5 over I times 2k pi. And we can easily simplify this a little bit real quick, because we can multiply both sides by I, and as a result we have I square in our denominator, and then I square equal to minus 1. So our sign, our basic sign of this x will be negative. So x equal to, we can write it as minus I natural log 5 over 2k pi. 2k pi. This is our answer. This is our answer to this question. And of course, we are talking about k. We're talking about integers. K is integers. We're talking about 1, 2, 3, and a lot of this case. And extremely important note right now: this root is great root for us when k is integer, but we don't know what will happen when k, for example, gonna be like a real number value. For example, k is equal to 1.2. We don't know what will happen right here. So it looks like a special case. We can easily reject this part. So this is our solution to our question 1 to the x equal to 5 when k is integer. We don't know exactly what will happen when k is real number, when k is negative. This is like a special case, because we are talking about, this is not like a huge amount of cases, huge amount of roots, because we reject real number root. So one and only case, we are talking about complex root, and we have at least one root. And this is extremely great. So let's write our final answer to this question. Here's our question, and here's our root. X is equal to minus natural log 5 times I. This is our complex root over 2k pi. And of course, don't forget about these restrictions. K is integer, and right here we have our answer. This is like a fun question, I would say, because this is like a question in terms of our identities. We can easily find this common thing, common patterns, and right now we can easily change this one by this expression that we found before. So this is like a special case, and I really hope you enjoy it. So this is my explanation to this question. I really hope you enjoy it. Also, write your thoughts, write your notes in the comments below. It will be really interesting to read about it. It will be really interesting to exchange information, and thank you for your time. Have a great day, and see you in the next videos.